So, what's the single most fundamental idea in all of computing? It's something called the bit. But to really get it, we're not going to start with a computer. Nope, we're going to start with something much simpler. Something you might even have in your pocket right now.
A plain old coin. It can only ever be in one of two states, right? Heads or tails. That's it. And it seems almost too simple. But believe it or not, this two-sided coin holds the secret to how everything in our digital world works, from sending a text to playing the most advanced video game.
Before we dive any deeper, I want you to just think about that for a second. What is the absolute most basic, can't be broken down any further piece of information? The answer is probably a lot simpler than you think.
All right, let's get into it. The answer to our question is found by looking for the absolute simplest way to store information. And as we're about to see, you really can't get any simpler than our coin.
Think about it. A single coin can only tell you one of two things. Is it heads or is it tails? That's all the information it has to give. Now, that limitation is actually its greatest strength. It makes it the simplest possible information carrier you can imagine. Let's put this into perspective. A coin has just two states. A standard die has 6. Now, obviously, the die can hold more information. But here's the key. You can't have fewer than 2 states. I mean, you can't have a one-sided coin, right? 2 is the absolute minimum. It's ground zero for information.
And that leads us right to the core idea we've been looking for. This is it. We found the fundamental building block. You could even call it the atom of information. It's basically anything that can exist in one of 2 separate states.
And here's where it gets really cool. It turns out this simple two-state idea isn't just about coins. It's a universal concept that literally connects the physical world we live in to the digital one we've built.
Once you see it, you start seeing it everywhere. A light switch, it's either off or on. A computer circuit, it's either a low voltage or a high voltage. Even the surface of a DVD stores information as either a tiny microscopic pit or a flat area called a land. Every single one of these is just a different version of our two-sided coin. And check this out. This is what that actually looks like. This isn't a drawing. It's a real microscopic image of a DVD surface. Each of those little trenches is a pit representing one state, and the flat parts are lands representing the other. This is physical information storage in its rawest, most beautiful form. Okay, so we've got heads and tails, on and off, pits and lands. To make sense of all of this, we need a universal language. So what we do is we abstract it. Instead of all those different physical descriptions, we just use 2 simple symbols, 0 and 1.
And that finally brings us to the official name for this idea. It's called a bit, which is just short for binary digit. This is it, the smallest possible piece of classical information, and its value can only ever be one of 2 things, a 0 or a 1.
So 1 bit by itself is incredibly simple. But this is where the magic happens. All the amazing complexity of our digital world, every photo, every song, every website, is built by just combining these simple bits together.
Just look at how fast the possibilities explode. 1 bit gives you 2 states. Add a second bit, you've got 4 states. A third bit, now you're at 8. Every single bit you add doubles your power. With n bits, you get 2 to the power of n possible states. This is the engine of the digital world, building incredible variety from a simple choice of 2. Now, these long strings of zeros and ones might look like gibberish, but they're actually numbers. You know how we're used to the decimal system, with a ones place, a tens place, a hundreds place? Well, binary is just a base 2 system. So instead of powers of 10, each spot is a power of 2. You've got the ones place, the twos place, the fours place, 8s, 16s, and so on. So for 11010, that's 116, 18, no 4s, 12, and no 1s. You add them up, and you get 26. Okay, so if we can represent any number we want using bits, that means we can use those numbers to represent anything else we want. So let's see how these bits can actually become a digital alphabet.
To make this work, all you need is a standard, basically a rule book that everyone agrees on. A classic one is called ASCII. It's a system that just assigns a unique 7-bit number to every single letter, number, and symbol. It's the decoder ring that bridges the computer's language of bits and our human language of text.
So let's take an example. If we go and look up the capital letter T in that ASCII rulebook, we'll find its code is this 7-bit binary number 1010100.
And if we want to write the word 2, well, we just grab the code for the lowercase o, which is 1101111, and stick it right on the end. You can see how we're literally building a word piece by piece, out of these binary blocks.
And finally, we add the code for M, and there you have it. To a computer, the name Tom isn't letters at all. It's just this 21-bit long string of zeros and ones. It's really nothing more than a number.
So getting a solid handle on this classical bit, this simple choice between 0 or 1, is the key to understanding all of today's technology. But it's also the launchpad for understanding exactly what's coming next. You see, on this next frontier of computing, every classical idea gets a quantum upgrade. And for the bit, the fundamental unit we've been talking about, its counterpart is something called the qubit. And let me tell you, this is where things get truly mind-bending.
We've spent this whole time establishing that a classical bit must make a choice. It is either a 0 or it is a 1. But the qubit, it plays by different rules. So what kind of new possibilities would open up if a qubit could be both 0 and 1 at the exact same time? Answering that question, that is the key to the next revolution in computing.